Properties of the mass spring oscillating system. In a mass spring system, and here's the mass, here's the spring, this entire thing is the system, a cycle is a full back and forth motion, which is the same as one trip around a circle in uniform circular motion. So let me just erase this. And what we're saying is if we were to start the oscillator here, and let's say we pull it out to this point here, then a complete cycle, once we let go, would be back to the original point and all the way back to where we started from. So that would be a complete cycle. So the period is the time it takes to complete one cycle. Frequency would be the number of cycles per second. So let's look at this picture to see what this is telling us. At this point, we're going to say we're in equilibrium. And then we pull it out to here, so the spring will be pulling us back. It comes through the initial point, then gets fully compressed over here. Now, is that a full period? No, we have to go back to this guy. So then it would go through here, then finally here, and then we have a full period, full back and forth motion. There is a point where the spring is neither stretched nor compressed. This is the equilibrium position. Right here where x equals 0. And there's no force on the mass from the spring at that point. We will measure displacement, which we're going to call x, from this equilibrium position here, x equals 0. Amplitude, that is where x is equal to capital A, is the maximum displacement. And continuing our comparisons to uniform circular motion, that would be the radius of the circle. The mass will oscillate between A and minus A. So let's erase this, and we would start it here. It would come over to here, where x is minus A, which is shown here. Then it would come on back to x equals A for a full period. The force exerted by the spring on the mass depends on the displacement, which is x, as given by Hooke's law. F is equal to minus kx, and the minus sign tells you that the force that the spring exerts is always opposite the displacement of the mass. So in this case, when the spring is pulled all the way out, spring force is this way, opposite the displacement, which was in this direction. In the middle, there is no displacement, so there is no force. And when it's fully compressed, when it's displaced to the left, the spring force is to the right, always opposite the displacement, and that's where that negative sign comes in. The minus sign indicates that the force exerted by the spring is a restoring force. It acts to restore the mass to its equilibrium position. The spring constant is K and represents the stiffness of the spring. The bigger the K, the bigger the stiffness, how hard it is to move the spring, how hard it is to compress it or expand it. The force, and therefore the acceleration, since F equals ma, changes continually with x. It is not a constant force. So a system that oscillates and is described by Hooke's law is called simple harmonic motion. The maximum force exerted on the mass is when the spring is at its most stretched or compressed position, where x is equal to either plus a or minus a, the amplitude. In that case, the magnitude of the force will just be K capital A. The minimum force is when the spring is at its equilibrium position and is not stretched or compressed at all. So x is equal to 0, so the force is equal to 0. The period of a mass spring system in simple harmonic motion is 2 pi times the square root of the mass that's oscillating divided by the spring constant. And this was derived in the unit presentation, so you can go back and look at that if you're interested. Frequency is 1 over the period, so it's 1 over 2 pi square root of k over m. Gravity does not affect the mass spring system. Let's consider a spring right here. It's suspended vertically. The only change is in the equilibrium position of the mass, so there's a slight change due to gravity, but the period stays the same. It is at this point here, the equilibrium position, where the spring force equals the gravitational force. So let's say it stretches down to here when you put a mass on it. So we have one force going down, mg, And the spring force is minus kx. And the minus just means you're in the opposite direction of its displacement. So we will now measure all our displacements from this point. We have a new equilibrium point, which is the only change here. So the effect of gravity is canceled out by changing to this new equilibrium position. Let's see what that means. We have a new equilibrium position because the mass has pulled the spring down. We will apply Newton's second law to the free body diagram. We'll take the up direction as positive. So the net force is kx0, and we're getting rid of the negative sign now because we're saying up is positive, and mg will be negative. That equals ma, but it's not moving, so that equals 0. So we have kx0, where x0 is our new equilibrium position, equals mg. Here is our new equilibrium position. It's a distance x0 down from the equilibrium position without the mass. So what is the net force if we now pull the spring down to a distance delta x and let it go? Well, down here, the net force is going to be in the up direction. F is equal to k times x0 plus delta x, because that's how much it's stretched from its original point, minus mg. We've got gravity going down again. We distribute the k, and we get kx0 plus k delta x minus mg. On the previous slide, we found in our new equilibrium, kx0 is equal to mg. So we're going to go ahead and plug that in over here. So now we have F net is mg plus k delta x minus mg, or the net force is now k delta x. The mass will now oscillate about its new equilibrium point, right over here, and its amplitude is delta x.